Hello, and welcome to another openFrameworks audio programming tutorial. Today, we will be building an envelope generator. The most standard configuration of an envelope generator is that of the ADSR, or Attack, Decay, Sustain, and Release. This envelope is set by setting the attack time, decay time, sustain level, and release time. This configuration has a sustain point, so if note's triggered on, it moves through the attack and decay phase, and then holds on the sustain until the note is let off. We will be building this in C++ and openFrameworks. So open the project generator. Decide on a new name. And we will not need any add-ons. Okay, so this will require a, well, not require, but would benefit from a separate document for the ADSR class, or the envelope generator class, excuse me. So if you're in Xcode, you can click on the source, right-click, new file. I'm going to call envelope generator. And we'll place this in the source folder. Okay, move to the envelope generator header, which is either H or HPP. We'll make a new class. Make space for our public variables and our private variables. And now we need to consider what variables we'll need for this unit generator. So we'll need attack time, decay time, sustain level, and release time. We'll keep track of our current amplitude value. And we'll need to replicate something like this gate that we have. So I will use an integer for that. All right, so let's make a constructor. I'll make some default values, so float initial attack, make it default to 80, float initial decay, we can make that default to 40, initial sustain, which we can make default to 0.7, and finally initial release. And this is all release time, attack time, decay time, sustain level. And we'll set that equal to 200 milliseconds. Right. We haven't done this in this series yet. When you make a constructor, if you set something in the constructor equal to a value, it will use that value unless the user using the class puts in a new value. So it's kind of a handy shortcut. All right, so do the easy part. Attack time that we're storing within the class equal to initial attack. Decay time from the constructor equals initial decay time. Sustain level equals initial sustain. And finally, release time equals initial release. Okay, so let's make a function to process the envelope generator. This will be called every sample to progress the envelope. So it's void process. That's what I usually call these sorts of functions. And then we'll also need a way for a user to get the envelope value back. So return a float, get value, return current value. And we could just make this public, but I've been told that it's safer to make as many variables private as you can, and then make getters and setters in the public space. Okay, so our process function is going to take up quite a bit of space here, so let's put that in the CPP. Process. Okay, so what the processing function will do will change depending on what part of the envelope we are on. So if we go back to this visualization, if we're on the attack, we'll have to increment the value a certain amount. If we're on the decay portion, we'll need to decrement the value by a certain amount. If we're on sustain, we don't need to do anything except keep this value the same. And if we're on release, we need to decrement by another amount. So this tells us a few things. We should have some kind of variable to keep track of which state we are in. So I'll make an integer. I'll call it state. And then let's make an enumerator to store our states in a readable way. So enum states. We'll have off for when there's it's not in any of those states. Attack, decay, sustain, release. Okay, so that's kind of stored neatly. So we can go back to our process function and make a switch operator to tell this to do something different depending on which state we are in. So switch, depending on which state, and then case off. So this has access to our enumerator. So this knows that off equals 0. Case attack, which is equal to 1. Case decay. In case, let's see, we'll need sustain. Not sure why I didn't do the appropriate indentation. And then case release. All right, and we could put a default here. Let's go ahead and do that for now, but erase it by the time we're done. And then if something goes wrong, the state is not any of these states, then we'll report that. So cout no such state envelope generator. Kind of give us a clue what's going wrong. It is a bad idea to put a cout in your audio thread. It will crash and destroy your audio thread. You won't be able to get anything accomplished because this function will halt the program until this is accomplished, and then you won't be able to fill your signal vector. But you know, that's not a problem now. It will tell us something's wrong, but this is not a good way to troubleshoot within the audio thread. Okay. So we have this. The process function will behave differently depending on what state we're in. We'll need a way to find out what state we're in, but let's get to that next. Let's start the current sample in our constructor at 0. Or sorry, current value, which is a sample, but equals 0. And then once we enter the attack phase, well, when it's off, we'll need to do nothing. We can just make sure current value equal to 0, but we shouldn't need to do that. And when we get to the attack phase, we'll have to add a value to our current value each sample. So what we need to do is make a function that will decide what that value is. We'll go over to our header. We can make this function private. So we will not need this function outside of the class. So we need increment values for all of our segments. Let's go back to this visualization. So we need to find out how much time we have in samples to get from here to there. And then after that, we need to find out what value we add each time to reach this point. So precision would be good here, so let's make these doubles. Attack increment, decay increment, and then release increment. Note that we do not need a sustain increment because that value remains static through the sustain period. Okay, so let's make a function called calculate increment. And then this will be different depending on which increment we're calculating. So let's make an input. Make an input called, let's see, what should we call this? State. Which state? All right, so depending on which increment we're calculating, the equation will be different. So we can do another switch. We get to do a lot of these in this class. Depending on what we put in here, which state. And then if we're calculating attack, do this. Okay, let's try to derive the function we need to calculate attack. So we need to find the incremental value to go from 0 to 1 over a certain amount of samples. Okay, so to find that, we need, say we wanted to go from 0 to 1 over exactly 1 second. That's a little easier to calculate, and we can start there. So for that, we would have 1 divided by our sample size, or a sample rate. So if we had 48,000 samples a second, we could have 48 point f. So that would, over 48,000 samples, we would go from 1 or 0 to 1. This value would give us. So we actually should store a sample rate now that I mention it. We'll store that as a double. And I always store the, in recent history, I've stored the sample rate as a double or a float because you have to cast it as a double or a float so often that it's actually more efficient to just store it that way, even though the sample rate will always be an integer. Sample rate, and we'll get that sample rate. We can put that in the constructor. Float sample rate equals 48,000. Okay. All right, so now we have the increment value if we're going from 0 to 1 over 1 second, having 48,000 divisions. So we need to adjust this based on the actual attack time. So if our attack time was 1, this would be fine, but it almost always will not be. So we need to multiply this denominator by our attack time, and then we'll convert that to seconds. So this, we're multiplying attack time by 0.001 just to convert milliseconds to seconds. So putting this in the denominator is going to, if our attack time is less than a second, this will actually decrease this value. So, right, so this will decrease the value. If our attack time is above 1 second, this will increase the value. I have that backwards. If the attack time is longer, then the increment will have to be longer. If the attack time is shorter than a second, the increment will have to be shorter. So this accommodates for that. This is our basic building block to get all the increments. So let's go ahead and copy this. We'll need attack increment equals this. And then our decay increment is going to be very similar, as will our release increment. Okay, so there is something different about our decay and our release increment. Note that I said the basic building block is 1 divided by sample rate, and then we need to scale that sample rate by the time of that interval. But that was to go from 0 to 1. These values are not going from 0 to 1. They're taking a smaller amount of space. The decay will go from 1 to some number, and the release will go from some number to 0. So it's only getting a portion of that 0 to 1 range. So what we can do to make this fairly easy is just make this number smaller to reflect that portion. So imagine that the sustain level is 0.5. Each one of these will have half the range. This will go to 1 to 0.5, and this will go from 0.5 to 1. So we need to make that increment half the size. So instead of 1, we need 1, put this in parentheses, 1 minus sustain level. Okay, so what this does is, see, if our sustain level is 0.75, then we only have a quarter of the way to go compared to what we have for the attack time. If our sustain level is 0.25, we have 75% of that distance. So this accommodates for that. And similarly, on a release increment, we just need sustain level divided by the same information. So this basically divides that time based on where the sustain level is, because if the sustain level is lower, that increment will have to be larger, going from the top of the decay to the bottom of the decay. But if the sustain level is just under 1, really close to 1, it won't have very far to go, so that increment will have to be very small. Okay, so I'm not sure why it's not letting me use C out here. It's interesting. I'm just going to get rid of it for now because we don't need that feedback anyway. Okay, so we haven't initialized our attack, decay, or release increments yet. So let's do that in our constructor. Attack increment equals, I'll call it calculate increment, calculate inc, and then this will be our attack. So that makes it kind of convenient. So our decay, oh, maybe, we'll see. Ah, I made this void, that was a mistake. This should return a float. Oh no, it shouldn't, sorry. This is an internal variable, so we don't have to return anything. This will set that here. So we don't need to set this equal. We can just call the function and it'll automatically set our increment value. All right, so we just need to put this for every increment. Calculate inc decay, calculate increment, release. All right, one mistake I made the first time I made the envelope generator is calculating the decay. I had this function right after decay. And there's a problem there. I'm calculating the decay, but I don't have the sustain level set yet. So it used that as 0 and my decay was off. So make sure you have initialize your sustain level before you call this function in your constructor. Okay, so we have our increment for each phase. Now we can go to our process function and make the magic happen. So if we're in the attack phase, our current value equals, or plus equals, our attack increment. All right, so that's just going up and up each increment. And then we need to stop that if our attack, or our current value reaches 1, we need to move to the decay phase. So if current value is greater than or equal to 1.0, let's see, state equals, well, first let's make sure current value is at 1.0 exactly. And then we progress to the next state. State equals decay. All right, so this will add and add and add until we reach the top, and then we're in our decay phase. When we're in decay, current value minus equals, since we're going down now, we're starting here and we're moving down to this level, minus equal our decay increment. Okay, and then we will break out of this when we've reached our sustain level. So if current value is less than or equal to sustain level, current value equals sustain level, then we need to move to our sustain phase. State, or sustain state equals sustain. All right, sustain is easy. We could just write nothing here. It won't help or hurt to add, well, hurt efficiency, I suppose, but current value equals sustain level. I'm going to write the whole thing out, even though we don't really need to do this for this. Whoa, that's all caps. All right, so let's write the release portion. And note that we don't move to release here. That'll happen if we get a note off message. So in release, our current value minus equal our release increment. And then we'll keep doing that every sample until our current value equals 0. So if current value less than or equal to 0 to be safe, current value equals 0, and then we'll switch to our off mode since the envelope is finished. So state equals off. All right, that is the process of this linear piecewise envelope. One thing we should do to be safe is set our initial state to off. All right, that will ensure that our current value remains 0. Now we have this hopefully fully functional envelope generator, but we have no way to turn it on or to turn it off. Okay, so for this tutorial, we are going to use keys A, S, D, F, G, H, J, K for an octave of sound. So when we push a note down, we'll tell the gate to switch to 1. If a key comes up on the keyboard, it'll tell the gate to turn off. So we'll have a function void set gate, new gate. And then we need to decide if it's a move from 0 to 1 or a 1 to 0. So let's store our previous gate. Equals gate. And then we'll set the new gate. Now we have storage. We have the previous gate and the new gate. So from that, we can tell if we made a transition from 0 to 1 or 1 to 0. And the reason I'm doing this is if we get multiple 1s and the envelope was already on, we don't necessarily want to restart the envelope, only for a new 1. So if previous gate equals 0 and gate equals 1, we went from 0 to 1, then state equals attack. If previous gate equals 1 and gate equals 0, state equals release. Okay, so now we have a way. What is? Oh, that's curious. Now we have a way to move from our main of app and of app header to trigger this gate on or off. All right, looking here to see if we've been thorough. I'm sure we'll find some issues. All right, so let's move to our header. Include the file we just made. And we'll make a new envelope. And let's try to compile, see if we get anything. Oh, we have 4 errors already. Oh, yes, this should have void. That should be a full colon. Yeah, I'm not sure why it's not liking my C out stuff today. Let's try this again, see if any of that clears up. All right, I thought the standard in and out library allowed me to use this, which I'm including here. Let's see if including the openFrameworks library helps. It's looking positive. Okay. Huh. Yeah, that's never happened to me before. But okay. Let's roll with the punches, I suppose. Yeah, if you're watching this and you know why that happened, please leave a comment. I'm curious. Okay, so we have our envelope generator successfully compiled, so that's a good start. Let's add our normal stuff for audio openFrameworks projects. We'll need an exit function. We'll need an audio out function. And let's move here. Let's set up the sound stream. Let's do 2 output channels, 0 input channels, 48,000 as the sample rate, and 512 is the buffer size, 4 buffers. Let's make our audio thread. And then we'll need our main loop here for int I equals 0. Loop through the whole buffer. And we'll need some kind of output. So we'll set buffer at I times number of channels plus 0, since we're on the 0th channel, equals current sample, buffer at I maple. And if we don't add our exit loop after calling it in the header, then it will not build. So void of app. We'll have to be responsible and close our thread at the end. Okay, let's go ahead and compile to make sure that all went smoothly. Seems good. All right, so let's grab some source. Let's, I'll put this in the description. Let's add the AudioTools header and CPP file to our project. Copy if needed. And I think in this version I have a sine wave oscillator. Let me double check. Yep, and it's called oscillator. So we need something to apply the envelope to. So let's do an oscillator. Oscillator. Set up. I'm assuming I wanted frequency first. Let's find out what I wanted. Go back here. Let's set this up right. So I shouldn't need to copy that. It should automatically gather it, but it's moving kind of slow. So our frequency, let's make 440. Phase 0, amplitude 1, and our sample rate 48,000. Okay. And let's just try to listen to that oscillator. That one's an old one, so I don't exactly trust it. Get sample, and we should hear a 440 hertz tone. Okay. Oh, I haven't included that file, so we need to include audio tools. Was it H or HPP? H. Oh, and I probably used the lowercase. You should make your classes uppercase. It's not a habit I've been into until recently. But I did this in audio tools. Now we look a little more comfortable here. Great, that is an oscillator. So now that's out of the way, let's set up our envelope. I just called it envelope, and I made this a pointer to an envelope. Envelope equals new envelope generator, and let's see if it tries to help me out. No. So if we leave this default, if we don't put anything in here, it'll give us all of our default values, which is really convenient. And our default values were 80 for the attack, 80 milliseconds on the attack, 40 for the decay, and 200 for the release. And our sample rate is consistent here, so that's good. All right, so every sample we need to process our envelope. So envelope process. And then now we need to multiply our current sample, which is a sine wave, by our envelope. Multiply it by envelope. This is not going well. Get sample. Get value. Okay. That should be fine. And now if we run our application, which I will do, this should sound like nothing. It should be multiplying this value by 0 every sample, so we shouldn't hear anything. It's a weird kind of success, but it is success. Okay, so if the key is pressed, so let's say if the key equal to the spacebar, envelope set gate to 1. So that turns the envelope on, and it will only turn off when that key is released. So if key equals spacebar, so this is the released callback, envelope set gate to 0. All right, so this should just be a 440 hertz sine wave. If you push the spacebar down, it ramps up, moves to the sustain point, and then once you release the spacebar, it ramps back down. So hopefully this works. Right now, press the spacebar. All right, so in a way, it's working. So it sounds to me like when I push the spacebar down, it's immediately going to the sustain level, and when I release the spacebar, it immediately going to 0. That's why we're getting these pops, these clicks. It's definitely not doing the envelope the way we want to. So let's see if we can find this bug. And let's make something a little more obvious, like a 200 millisecond, and we can leave that at 40. And let's do like 800 millisecond release. Likely something has not been instantiated. If our process, get value. We should set our gate to 0 when we start, but I don't think that's what's causing the problem. It would cause a problem on the very first one, but it should fix itself. Okay, well, I found one issue. This should be decay time, and this should be release time. I forgot to adjust those after I copied and paste. That is one of the many dangers of copy and paste. Let's see. I still think there is another issue. Right. So we still have another issue. This would have caused some headache later, but this would just make our time values inaccurate. It shouldn't cause this click and pop. Ah, okay. Found it. So we are dividing by our sample rate in this function, but we are not getting our sample rate until after we use these. So let's move that here, and we'll have a successful envelope generator. Okay, great. Now let's do something fairly simple. We should make a 1-octave keyboard with our keyboard. So we'll use one oscillator. We'll control the frequency with a smooth value. So smooth, this is from another tutorial linked above. Value equals frequency. We'll set that up in our setup function. Set it to 440 at the beginning, and then we can do or set up our smoother. Our frequency dot smoother equals new. And we'll do a 40 millisecond time here. Actually, let's do 100. I'm going to check this audio tools file and make sure we actually have that there. Parameter smoother. All right, we'll need to add the sample rate on this version. (100 milliseconds) and 48,000 as our sample rate. And what is it sad about? Again, I didn't name my class with a capital letter as I should have. So, okay, moving on. Our envelope will process that there. We'll need to set our frequency current value. So frequency.current value equals our smoother. And we'll process our target value. And this will be important because we don't want to change frequencies instantaneously. You'll get a pop or a click by doing that. Assuming our oscillator has a set frequency function. Oscillator set frequency, or frequency.current value. Okay, so now we'll do a switch here. Switch key. And I'm going to fast forward through this, just because it's a little redundant. Okay, so copy this to your key up line. So we'll need each one. And then here we can set, we'll set the frequency dependent on which key is pressed, and then turn the gate on. So let's make a function. It will return a float called MIDI to frequency. This will make this a little bit easier so we don't have to get a chart out of a C major scale. So we'll input a MIDI value, which can be an integer or a float. You can do halfway through a MIDI value if you're not actually using MIDI. And this is how I usually find how to do this. MIDI to frequency. I forget how to do this off the top of my head. Here it is. All right, so I'll comment this out and use it as a reference. All right, so this returns power, or 440 times the power of 2 to the input, which here I have as MIDI val, minus 69, which is the MIDI number for 440 hertz, divided by 12. I'll put parentheses around these to make it clear. And 12 is a float. So here we're good. So in this, let's decide what base frequency we'll want. 60 is middle C, so let's go down an octave from that. So that'll be 48. Frequency target value equals MIDI to frequency, what did I say, 48. And we'll add this, go from C to D, so 2 more, 50, D to E, 52, E to F, this is 53. We'll have F to G, so that's 55. G to A, which is 57. And A to B, which is another 2, which would be 59. And then B to C, it's a half step, so up to 60. We landed on the next octave. So C major scale. Also for each one of these, we'll want to turn the envelope off. So, or on, sorry. So envelope, set gate, 1. And for each of these, we'll want to turn the envelope off. Okay, so this all looks happy. Let's try to run it. It won't work. We need to put our semicolon here. Okay, so my ASDF don't work. G, H, J, K is fine. That's interesting. What have I done wrong? Actually, it may be the case that they do work, and I can't hear that on my MacBook speakers because it's too low of a frequency. That's a possibility. These don't do low frequency well. So I'm going to plug in and find out. Okay, I'm back. I had a technical difficulty. I changed output device when I plugged in my headphones. That changed automatically, and none of my sound output from openFrameworks was being captured, and I did not know. So I'm back. While I was gone, I did add portamento. I just changed our frequency smoother value to 500 milliseconds, so there's a noticeable drift in frequency. The parameter smoother is pretty well suited to be a portamento device because it doesn't move linearly through the frequencies, so it's kind of a nice curve, a more natural curve. So we have our finished envelope. It seems to work just fine. Note that this is a linear piecewise envelope. These are very efficient, and they're very good for controlling things such as filter or queue of a filter or index of a frequency modulation synth. They are not well suited to control the frequency of an oscillator or to even control the amplitude of a sound. These are used fairly often if you're in Max MSP and use their standard ADSR. This is a linear piecewise envelope, and I think I crashed Max just doing that. Good old Max. Cool. But yeah, so it's used a lot, but it really shouldn't be used often to control the amplitude of a sound. The reason being, amplitude is not perceived linearly. We're moving from 0 to 1 linearly, but we're not going from infinitely quiet to infinite, or to our maximum loudness linearly. It's perceptually non-linear if we're doing it linearly. So for a future tutorial, we'll come back to the envelope generator, and we'll make variable curves depending on the needs of this generator. There's analog styles. There's a couple of different styles. We could cater to the specific needs if we want to model the old analog synths. Those are just the charging and discharging of a capacitor. We can do that. If we want it to be perceptually linear for controlling frequencies, or perceptually linear for controlling loudness, then we could do that as well. And this is significantly more complicated, and it is a bit more computationally expensive. But if you're using an envelope to control amplitude, it really should be a curved envelope. But this does work satisfactorily. I mean, it's fine, but it could be better. So until then, thank you.